So I'm Sam Smith. Forget that name, then my parents wasted their effort. I'm the founder of the Reputation Spoke. So I'm going to give a little bit of an AI overview, just so I get a sense of the audience. Who in here has actually had like a class in AI? Something machine learning. Okay, a handful. All right. Who in here has actually done like significant work, like you build a system? Okay, what did you build?
I've got a deep learning before. I was doing deep learning before training.
Oh, okay, you're doing deep learning. Okay. Okay. So did you use a toolkit like Keras?
Well, mostly using Keras and so.
Yeah. Okay. All right. Great. So some people have a little more familiarity. But this is a non-technical session, at least in terms of the math. It's fairly technical in terms of architecture, because I think the point is for you guys to get an overview of how AI might be useful in your applications. And it's become really popular lately, but I'm going to talk a little bit about the landscape of AI and give you a sense for that. And if you have questions, feel free to ask questions. So, we see this term AI, and actually for me, it's kind of an offensive term, right? Because people overuse it. They use it to mean lots of things, and it's become popular. So this is the definition I use for AI. It's computing techniques that attempt to replicate various aspects of human perception and cognition that is only taught to graduate students. I added that, right? Because, 20 years ago, relational databases were AI, right? Now they're just a thing you use. And I would say now that something like deep learning is not AI anymore, because you get it in undergraduate school. I know lots of undergraduates that take a class, and they learn how to use like a Keras toolkit. There's lots of toolkits. You don't have to have a deep understanding of what's going under the hood to be able to use it.
You cannot actually train a good model if you don't understand.
That's right, but still people think they can,
yeah.
right? And so they have data science boot camps. So in 6 weeks you can be a data scientist, right?
Right.
It's like,
that's right.
Yeah. So that's what I'm saying. That's exactly right. You really can't.
I've got so many posts on Facebook saying that you can become an expert in deep learning or machine learning in only 6 weeks by reading only 3.
Yeah, exactly. So that's what I say. So there are now undergraduate classes where you can learn deep learning in an undergraduate class, and you might spend a few weeks, building a couple of toy models, and now you know what it is. So most AI is what we call weak or narrow AI. And what that means is that it's not, and I'm using the term AI in a very general sense, right? It's sort of like, it really is just computation. It's just computation that uses certain techniques that for most people you have to have advanced training to get. It's not, there's no magic here, it's just you're using certain mathematical things and you're doing computation with them, and it takes a little bit more time and effort to understand those, and it's not something that most people are exposed to. So it's been popularized as AI, and AI equals magic, and I'm just saying, I'm using the term AI, but I don't like the term. Yeah, you have a question?
Why do you emphasize human perception and cognition?
Because that's where the artificial intelligence came from. The idea was, we know humans are really smart. They can do things, so how do we make computers think like people, right? Back in the 50s and 60s, that was when AI was coined, that was the approach. Make computers think like people. Because people can do these amazing perceptual things, right? So one of the reasons deep learning has become popular is because it was an example where you could have a computer do things that were human class for the first time. They could do image recognition that was as good as a human, or close to it, in narrow context, right? Whereas for the previous 30 years, just bad. It kind of worked, and people would claim that it worked, but then it was easy to defeat it, so on, right? So narrow AI means the context is sufficiently narrow, the problem constraints are sufficiently small, that the outliers, the exceptions, the assumptions are all enough that you can control them, that you can get your machine learning algorithm to work reasonably well and get real good results. And as soon as you vary from those parameters, it stops working. There is an effort now for people to build what's called general or strong AI, which is AI that doesn't have those constraints. And there are a lot of people working on that. Singularity.net, which is a recent blockchain that did a 50 million. You know, Ben Gertzel, he's a strong general AI guy, wrote lots of stuff. And there's a lot of work going on there, and a lot of hype, and so I don't really care about that because it's not really useful in most cases. It isn't really solving problems, and then maybe there's some strong AI guys in here, and I don't want to get into a flame war over it, but let's, for most people, the narrow AI is what is practical now, and the general stuff is not there yet. So there are many types of AI. And that's where usually most people don't have an exposure. They don't understand that AI is not just deep learning. It isn't just that. In fact, there are more AI that's not deep learning that is probably more useful to what you guys, the problems you have to solve. And I think that's the perspective that I want to bring up. And the first I put up here is called automated reasoning. Who in here has heard the term automated reasoning? Besides my two guys. Okay, a couple of you, right? When I say the term automated reasoning, what does that say to you?
I think about automated mathematical proof, for example.
No, that's not what it is, but that's okay, right? So there's formal methods that is that, right? So the thing is that it is a thing. There are thousands of papers on automated reasoning. There are whole subfields of automated reasoning you've never heard of, right? Unless you've actually done research in the field, because it just isn't common knowledge. But it's probably the most useful. There's machine learning, you've heard that, right? Because that's another euphemism for AI. But machine learning is just a type of AI that has a type of learning, right? Automated reasoning doesn't necessarily have to have any learning in it, but it's still reasoning like human class cognition. It just doesn't learn. Machine intelligence is another term people use to get the artificial out of there. The machine does it. Computational intelligence, another term. These are all terms that have subfields that people use. There's artificial general intelligence, we talked about that already. There's natural language processing. That's one of the more popular ones, right? Some of you probably have done natural language processing because it's used a lot in user interfaces now. Computational search. Computational search is algorithms that allow you to search your knowledge and representation to come up with data. There's pattern recognition. So what is deep learning? It's primarily pattern recognition. Image processing. There's a whole field of image processing. There's intelligent control. Have you ever heard of that? Right? Artificial intelligence for control. That's actually my background. I'm an automated reasoning intelligent control person. Reinforcement learning. That was another one that's really popular, and it's like deep reinforcement learning, right? Hybrids, these work. Meta learning. Have you heard of meta learning? That's learning how to learn, right? So it's sort of halfway between the narrow AI and the general AI camp. It's sort of like, well, we can do a little bit better, right? Deep learning, artificial neural networks, fuzzy logic, genetic algorithms, evolutionary algorithms. You know the difference between a genetic and evolutionary algorithm? I'm not going to answer it. Right? Bayesian belief networks, symbolic reasoning, approximate dynamic programming. That's also a field that I've published research in. Expert systems, right? These are just some of them. There's like another 20 or 30 easy, right? If you went and did the research, you would find thousands of papers, hundreds of books, people that their whole career have been doing work in these narrow fields just to advance the needle to get a little bit better machine intelligence. So the question is, if I'm sampling the AI space to solve my problem, and my only sample is deep learning, what have I done? I've biased my data set, right? I basically said, all of the problems I want to solve look like a nail because I only have a hammer as a tool. And the purpose of this talk is to at least expose you to the fact that you may be needing a different tool besides a hammer. And don't limit yourself to saying, well, just because I can go online and find tutorials, I can find books, I can find free toolkits that allow me to do deep learning, that's all that I can do. So I'm not going to go through this whole thing, but this is available online. If you just look up the machine intelligence landscape, you'll find it. But you can see a lot of these different, these are all companies in this space, and almost all of them have a specific toolkit, a specific set of AI technique that they're applying to a given problem. And only some of them are using deep learning. Many of them, most of them aren't using deep learning. And so that gives you an idea of the landscape, right? Google, Amazon, Facebook, deep learning. The rest of these people not. They're using other forms of AI. So the information is out there, you just have to look for it. And then there's this one. So if you look up the many trades of AI, there's a nice blog post on this. And so here's the other thing. Each subfield is filled with people who are advocates for their field. They're true believers in their tribe, right? So if I go to a conference and I want to solve a particular problem, and I say, oh, I'm going to solve a fuzzy logic, and there's a Bayesian person next to me, right? We're going to have a very interesting conversation. You know? And either we're polite to each other or we're not. And if we're not polite, you know, then it turns into a flame war because, you know, especially the Bayesians have really strong beliefs, right? Any Bayesians in here? Okay. That was right. So you have different approaches, and people become experts in those approaches. And here, and I think I have another slide, but I'll say it now. It's usually better to be a proficient practitioner in a given technique than the particular technique you use, because many of these techniques are isometric. They're equivalent techniques. They're universal function approximators, so it doesn't really matter. But if I'm good at one technique, I can get more out of my data and I can get better results. If I'm just poor, you know, at the technique, then it doesn't matter which technique I won't get good results. So proficiency is as important as anything else in this approach. So let's talk a little bit about deep learning, right? It's a supervised learning using multi-layer backpropagation with a stochastic gradient descent learning algorithm on pre-classified training data. That's the core simple thing. And then there's lots of branches of deep learning. There's recurrent networks. There's convolutionary networks. There's all different structures with various things. But fundamentally, the fundamental constraint is that I have to have a system that I can use that technique on. And a stochastic gradient descent means that I have to have a continuously differentiable system. And so there's only a subset of real-world problems that are continuously differentiable. But it does work, it's popular, it works with large data sets, and it's a simple algorithm. It's low-hanging fruit. It's like in the 80s, it was like the first thing people thought of. Oh wait, backprop with 2 layers, and the math is simple enough that I can build a simple recursive description of the math. Now I can actually compute it on a computer that in 1987 would have been a 20 megahertz 6820, right? With a couple of maybe a meg of RAM, at best, a few hundred K of RAM. So that works, right? So fast forward 20 years, you have petabyte data sets and multi-gigahertz computers that are networked with GPUs, and all of a sudden that simple algorithm now can chunk through those petabyte data sets in finite amount of time. Right? Back in those days, it was like, well, to really use neural networks, I would need computers that won't exist for 20 years. Right? And so people started developing other systems that would work better with sparse data. So if your problem is a pattern recognition image classification problem, then that's a really good selection. There are other ways to do that. There are other toolkits that work, but that's not a bad one. So here's something up here that under that spectrum, and I'm putting up here things that are human class. So deep learning has solved some human class problems. This is another one. This is a genetic fuzzy-based aerial vehicle control. And this is a recent paper, and this system, and understand this is not a very useful diagram because A2 in the paper explains what A2 is, but you notice there's enough blocks, each block has a different function. So instead of being a monolithic stack of layers that you don't know what are in the layers, this is a hierarchical decomposed stack, and each one of these is an independent AI that does a specific task. and then they're hierarchically combined to come up with the output control action. So this is actually in the field more like automated reasoning. This is an automated reasoning type approach. This is the stuff that is automated control. Yes?
So is this architected the way those components fit together, or that was?
Yeah, it was. No, it was architected over time. So they started out with a simple system. They did lots of simulations. They had humans. So this was built over a couple of years, where they'd bring in pilots. They would fight it. The pilots would win. They would use that data to update their AI to learn from that interaction. And after they had done it, they reached the point to where this wins every time. The best pilots cannot defeat it. So it's human class. So if we put this in a fighter jet, we win every dogfight. We no longer need human pilots, right? That's human class. That is a big result, and it's not deep learning, right? So I'm just saying that because don't believe the hype, right? There are ways to get human class, and some of them, and there are different approaches. And in many of our cases, this is better because you can decompose it. You can modularize it, refactor it. You can take a lot of what's learned here and apply it to a different class of fighter fights. But if I have a deep learning system, I change anything about my data set, I can't guarantee any kind of performance results. So it's a fragile, it's a narrower approach. Yes?
Can you just make a comment? Like, as you're going through this, all of the blockchain smart contracting stuff that we do also kind of applies like monoliths or something.
Yeah, that's right.
So it's like,
yes, absolutely. So that's why I say it's an architectural thing. So what you're trying to do with blockchain, what people are trying to do with blockchain, is they're trying to build an AI, right? It's not a pattern recognition AI. It's an AI that's doing something else. And actually, we're going to talk about that, right? So part of my talk is to sort of set the stage and then talk about AIs for what we want to do. So there are three basic types of learning types. So now we've narrowed down to just machine learning. We've thrown away all the other ones, and now we're just talking about the ones that have machine learning. And the basic types are supervised. And supervised means that I have a data set, and then I manually go through the data set, and I say, that's a picture of a basketball. That's a picture of a basketball. That has a basketball in the picture. That has a basketball in the picture. And I get a petabyte of pictures with basketballs at different sizes, different orientations, different lighting, different color, different backgrounds, right? And then I get a bunch of other pictures that don't have basketballs in them. And now I've got this binary training set where I can say basketball, not basketball. And then I run that through my system multiple times, and I get, when I'm done, a classifier that if I give it a picture that I haven't shown it before, that has a basketball in it, it has a really high probability it'll say basketball in the picture, right? Which used to defeat every AI image in the past, because if I just change enough of the scenery, the background, but even now, if I put random noise in the image that the human can't see, it'll fail. It won't be able to classify, because the humans are that much better at classification than even the best trained deep learning AI. So understand your limitations, and that's what you were saying, right? You were saying if I don't really understand the limitations of my data set, just because I read a tutorial and I know how to feed data into deep learning, doesn't mean I'm going to get the results I want. Yeah. Unsupervised learning. Unsupervised learning, what that is about is that I don't have a training data set. I haven't been able to classify and say this is A and this is B, and I want to distinguish between the two. What I'm trying to do is I'm trying to look at my data set and learn what the data is. And so the primary thing is called clustering. So what I'm saying is I've got a bunch of data, and if I put it in my feature space, which, let me describe feature space. Let's say that I want to classify basketball players. And basketball players have a height, they have a weight, they might have what college they played for, what types of defenses have they learned, what sort of offenses have they learned, different things that distinguish them. So that's my feature set. So now I take all the basketball players and I graph them in that feature space, right? This multidimensional space. And now when I graph them in that space, there are going to be some basketball players that are close together in that feature space, and other ones that are further apart, and I might have groups. And if I can distinguish those groups, and I say those are clusters, and that gives me some meaning, I can extract some meaning from that. And that might be useful in classification because I don't have a training data set. I'm trying to discover my classes from the data. And then later I can bring in new data and say, well, he's closer to this cluster center, so he must be in this class of basketball player. So that's why it's unsupervised learning, because I didn't have an oracle that went through and said, I know what this is and this isn't what it is, right? It's like, I don't know, I'm trying to learn. The third one, so these are the primary ones, there's lots of other ones, right? Is reinforcement learning. And so we're going to talk about these in a little more detail. Actually, let me go to this slide. Okay, so supervised learning model. Can you see that? Is that too small?
Too small.
Too small, okay. So here's my training data set. Here's my features. So what I do is I take the training data set and I extract features from it. I label my data sets. And then I apply that to my machine learning algorithm. I come up with a model that is supposed to predict what something is. And then I apply untrained data, generate a feature vector, and then I get an expected label out. Right? Yeah.
Can you explain the feature vector?
So what I just said for like a basketball player, the different features, height, weight. So if I have a vector, I have height as one element, weight as another element. So now my feature space is on an axis, I have height on one axis, weight on another axis. So that's a two-dimensional feature space, height and weight. So I could have a 20-dimensional feature space or a 100-dimensional feature space. I mean, if I have a database and I have a record in the database and I have name, address, phone number, every field in that database could be a feature. And so that's my feature space. And so feature space design is one of the things that's not automated yet. Right? If I don't know how to design my feature space, my learning algorithm won't work. So that's where it goes from, yeah, I can go to a coding boot camp and I can learn how to stick data that's been labeled into a thing and get an answer. But if I don't do the labeling right, I garbage in, garbage out, right?
The labels match the features? Or?
Yeah, no, the labels are where I'm assigning a given item in the data set to a given class. So I gave you the example of basketball, not basketball. I might have 20 classes. So each feature vector in my data set, I assign to a given class. And then I train against those classes. So I might have a multi-class classifier that says it's not just basketballs and not basketballs. It might be basketballs and footballs and volleyballs and tennis balls and combinations of them. So for example, this is a very simple two-dimensional classification problem. So I have a two-dimensional feature space, and here's maybe my training set, and this is my control set. And what I want is to find that hyperplane that divides the two so that when I get something that looks like these, it classifies it as belonging to this side and not that side. And then if I have multi-dimensions, I've got to have a multi-dimensional hyperplane. And if it's really complicated, it's not a hyperplane, it's a piecewise continuous intersection of multiple hyperplanes, right? And that's why it's hard to understand what's going on, because I've got a 20-layer neural network, and each layer is building different planes that then are part of other planes. So where are we? Oh, okay, unsupervised. So unsupervised is that I have my training data set, I get my features, my machine learning algorithm, this clustering algorithm, builds a predictive model. Notice I didn't have any labels, and now I can input stuff and get out, where it's grouped with. And so here's like, I just plot all my data, and I look at this and I say, well, these guys look like they belong to something. So I generate the labels from looking at the data, right? I don't have an oracle that says, that's a basketball, because it may be that I plot it up here in a supervised thing. I might have a basketball in here amongst a bunch of non-basketballs, and I'm going, how did I get a basketball in with the non-basketballs? Well, it's because my feature space is wrong. I need another feature. There's something I missed, so that I can have another feature space that keeps that basketball out of that grouping. So, and then the final one is reinforcement learning. So reinforcement learning is in between the two. Reinforcement learning, you use an objective function. They call it a critic here. You're using some piece of software or some algorithm that isn't labeling things as yes or no, basketball, not basketball, but it's saying something like you're getting close. So for example, I might say, you know, and usually you're doing things where you're having states. You're going from state to state. So it doesn't really work for image classification. It works for things like decision making, like games, like AlphaGo, right? I have a current state. I want to decide what the next move is to get to a different state. So what I have is I have a critic that says, well, okay, you know, I know chess better than Go. So say I'm in chess, right? And I have a particular board pattern, and if I do a trade of a bishop for a queen, I'm in a better position. Now I may not win the game, but I'm in a better position. So my critic would say that's a better thing to do. So if you have an opportunity, do that. But the problem is that if I always do the optimal thing, given my current state, I might get trapped in a local minimum where I can't win. So I have to moderate that by every once in a while, and it's usually parameterized, I do an explorative move. I do a random move. I say, well, yeah, the optimum move in this state would be to do this, but I'm never going to learn anything if I always do the optimum given my critic, because the critic's stupid. So now what I want to do is I want to try something that I've never tried before and see what the response is, and if I actually get better, according to my critic, or according to my evaluation function, then I remember that. So that's how I'm learning. I'm learning by exploration. So reinforcement learning is really powerful, especially if you don't have any data, because you're generating the data set on the fly. Yes?
Does it make that random choice in proportion to how many times it will lead to a successful game? So like if
yes and no,
50%,
right? You have fixed ones, you have variable ones, you have adaptive critics that have an adaptive critic, right? So you can have an infinite regression of adaptive critics. And some people say, well, that's what humans are, is an infinite regression of adaptive critics. And that's how we get general class intelligence, is it's not just one critic, but every critic has a critic, and you know, at some point you converge to something, right? But it's a very powerful learning technique. So combining this with something else allows you to generate your training data on the fly. And so, for example, in the application we have where it's reputation, are we out of time already? No, we're halfway through. Okay. If you don't have data, but you have people interacting on the platform, you can use reinforcement learning to improve your performance just by observing how people are behaving on your platform. And you just need a simple critic. You need some simple objective function that says, yeah, this was better than what was before, or this was worse. And then you can say, we want to remember this, we don't want to remember that. Right? So if you find yourself approaching problems and you see that the data that you have fits one of these three scenarios, then that guides you into what class of machine learning that you want to use. Oh, I'm going the wrong way. What did I do that for? Really bad adaptive critic here. Did escape out there. There we go. Common concepts. So I already talked about this, but most of the learning methods use some form of stochastic gradient descent. This has a really hard limitation, that your whole system of learning has to be a continuously differentiable function. That's a very narrow subset of real-world problems. One of the reasons humans are much better than machines in general is that we are not limited by that. We can figure out how to learn without having a continuously differentiable function. Right? But man, if I want to write a paper and show convergence properties and show how well it performs compared to other stuff, then man, having a continuous difference function makes my life easy, which is a problem. Because people tend to do the easy thing. The thing that they can put hard numbers around and say, yeah, we know this works. And people criticize you if you don't do that. They say, well, how can, I run into this. Well, how can you do verification if you don't have, a closed form solution to that? And it's like, well, yeah, it's a problem, but if we ever want to get more robust AIs, we have to be able to live not in that space. The other thing is, I mentioned this, universal function approximators. What that says is that if I need a continuous geometric function, then anything that's a universal function approximator can be a representation. I can implement it. They're isometric. So it doesn't matter if it's a neural network or fuzzy logic or a genetic algorithm. if under the hood they're a universal function approximator, they will get the same result if I train them hard enough. And so now I'm not talking about how good they are, I'm talking about my training methodology. And how fast do they converge, and how easy do they get stuck in local minima, and how do I inject noise and stuff like that. And now I'm in the changing the, what's the phrase, positioning the chairs on the deck of the Titanic, right? The same result's going to happen. The ship's going to sink, and it doesn't, or I'm going to converge to an answer. So don't argue with me that Bayesian belief, because a Bayesian belief network is a universal functional approximation. So yes, I agree with you that it will, you will get answers if you know how to do learning on Bayesian belief networks, and you're really good at it. You can make it work. There's something called the no free lunch theorem, and this is the thing that's counterintuitive to most people. And I have the words there, but I'll just explain it. When I build a machine learning algorithm, the algorithm itself contains all the information that I'm going to get as an answer. In other words, I'm not going to discuss, so information theory, Shannon information, I'm not going to get any more information out than I put in. What that means is that picking the algorithm for the problem is the problem in most cases. The right algorithm will be adapted to the problem well enough that I get useful results. So the no free lunch theorem, the proof of it is based on that if I take any learning algorithm and I have a class of problems and I apply that learning algorithm to a whole family of problems, on average, the results will be no better than random chance. So I'll get a peak of performance on this problem, and on this problem it'll be really low, this problem will be halfway this way, and on average, it's just random chance. So if I want to have a general learning algorithm, I can't do it. It's not possible. I have to use a learning algorithm for each different problem space. So when people say I have a hammer and it will work on every problem, no free lunch theorem says, no, that's not going to happen. Just disabuse yourself of that notion. So I already said this, proficiency practitioner is more important than the method used if the method is appropriate to the problem type. So if I'm doing stochastic gradient descent on a continuously differentiable function for image classification, any universal function approximator will work. But if I'm trying to solve a problem that I don't have, a labeled data set, and it's not, then I have to use a method that works in that case. So stochastic gradient descent. Very little math here, right? The W is your parameter space. So if I have a system that's governed by parameters, that my model that says I'm going to predict an output, and the parameters determine the prediction. So I have my system state, I feed it in, there are parameters to my model. Maybe it's a polynomial, like for example, like this is a polynomial. And then if I change the parameters, I change the shape of the polynomial, right? So I'm trying to learn the parameters of the polynomial. That's the W. And so what I'm doing is I start at an initial space in my parameter space, and I've got a big error. That's the height here is the error. And what I do is I compute the gradient relative to my data set locally to a subset of my data points. It might be one data point, usually it's some group of data points. And I compute a gradient, and I say, well, in this direction, if I move my parameter by this delta, my error for this subset of data points decreases. So I'm gradient following. And the fact that I'm using a subset of my data set at any point in time to compute the gradient means that it's stochastic. It's noisy. And that's an advantage, not a disadvantage. Because it allows me to skip over local minima, because the noise says one time I'll go this way, the next time through my data set I'll go this way, or the next part of data will give me a different direction. So eventually I'll reach a point to where my gradient is 0, and then I've hit a local minima or hopefully a global minima, and I'm done learning. And it might take a long time, it might take a short period. So this is like a two-dimensional. You can see this one's jumping around, which is what it normally looks like. And here's you might have local cost minima. So one of the approaches people use is that I get in a local minima, I inject noise, right? There's something called simulated annealing, which is another learning technique, which we haven't talked about. And simulated annealing is basically just randomly modify things, but have a schedule that the random modifications reduce in amplitude. So simulated annealing is like you apply heat. Heat makes the molecules move. As it cools off, the molecules stop moving, and then they sort of solidify. So the molecules in this case are your parameters. You're just trying random values of parameters. You're just randomly picking them, evaluate and say, well, is that good or bad? You know, if it's good, you keep it. If it's bad, you throw it away. And then the amount of randomness decreases with time. So a lot of times to make these things work, you have to use a combination of like a simulated annealing plus your learning approach, because you have to direct randomness to get out a local minimum. And that's where the art comes in. Because it's like, oh, I can't just apply it, it just works. I keep getting stuck in local minimum, and I don't realize it. So let's talk about what you really care about. New kinds of AI for the blockchain. We want artificial social intelligence. Right? We're social beings, we're interacting. Most of the applications in consensus involve humans at some point. And humans are really good in interacting in networks with other people. Machines just don't cut it. So how do we make it so that machines can interact socially, politically, and do things? Well, reputation is all about that. One of the things humans do really well is they keep track of who screws them over, and they remember that. And they keep track of who they can trust. And they build social networks that they use to make decisions. But when we go to the internet and we lose that social connection, it's easy to trick people. They don't have ways to moderate that, so we have to figure that out. Artificial network intelligence. It's the same thing, but now it's not social. It's just the fact that we have a bunch of nodes interacting on a network, and they're distributed, they're decentralized. And these nodes might be agents that all have different goals and objectives, and how do they work together, right? So if I have competing goals and objectives, what's the branch of AI that works with that? Anybody know? Multi-objective decision making. Have you ever heard of multi-objective decision making? Oh, yeah.
Yeah. So
Yeah.
You have so in the reinforced learning slide there was a critic objective.
Yeah.
So multi-objective
Yeah,
is working with several objectives.
And they might be competing, right?
And finding a balance between all of
Between
them.
them, right. So the critic is doing automated reasoning. So you have an automated reasoning critic that is doing a reinforcement learning algorithm. So what really happens is that automated reasoning, which are the rules by which components of your system make decisions, tend to be hard-coded. You have to code them. They're heuristic. They're based on things. But you can't build any of these learning systems without some degree of automated reasoning. People tend to be really weak because they don't study how to do automated reasoning well. They use very simple things because it's too much trouble. Group AI, right? What is distributed consensus? It is group AI. It is how groups make decisions. How do groups of people make decisions, right? Making a computer think like people. Well, we make decisions in groups in different ways. We can make machines that make group decisions. So group decision making, there's a whole subfield of expert consensus, and we'll talk about that in a little bit. Decentralized AI, distributed AI, all need identity, reputation, distributed consensus. So that's my thesis here. To do any of these, you've got to have these. So I know Joe Lubin in the Paris town hall said he thought self-sovereign decentralized identity was going to be a core foundational thing. It's because it is. It really is. You can't do any of these network things if I don't have identity. Because if I don't have identity that's anchored in a credible source, then all of these algorithms start to fail easily, right? And an identity is no good without a reputation. And I can't have a reputation without an identity. So I gotta have both of those. And now, how do I make the group decision making robust? Distributed consensus, right? So those three are the foundation layers that we need to build any kind of network, social intelligence, group AI. We need those. And so if you're building an app and you need any of this, and you don't have this, you're likely going to have a lot of heartache. You're going to run into walls where you say, oh, it's not going to work, or it's going to fail for these reasons because you haven't built the foundation. So distributed consensus. Everybody here knows what proof of work is. Everybody knows what proof of stake is. How many people in here know what Byzantine agreement is? Really? How many people have heard the term Byzantine agreement? Okay, all right. At least you've heard the term, right? How many have heard Byzantine fault tolerance? Okay, a few more, right? Okay, so Byzantine fault tolerance comes from the field of Byzantine agreement. It just so happens that proof of work is also Byzantine fault tolerant. But there was 20 years of work in Byzantine fault tolerance before proof of work came out. Proof of work solves elegantly a specific problem in distributed consensus, and that is the Sybil attack problem. That's what it solves elegantly, right? Everything else it does not solve elegantly, right? Okay? Right? So proof of stake is an attempt, it's asymmetric proof of work, is an attempt to make, while still solving the Sybil problem, to make increased transaction rates, lower latencies. Byzantine agreement does not solve the Sybil problem elegantly. That's its main failure, right? But it solves everything else really well, right? So now the problem is, how do we solve problems that have different feature sets in terms of their breakdown between scalability, number of transaction costs, latency, credibility, things like governance. Each problem set has a different feature set, different mixes of those. So one size fits all doesn't work. It's helpful to understand those so you can make those trade-offs. And there's a final one that I know almost nobody's heard of. It's called coordinated control. Anybody heard of coordinated control as a distributed consensus algorithm? So this predates all of these. People were doing this well, actually, this was pretty old too. These are probably about the same. But this had a lot more work. There are a lot more papers in this, and a lot more research done it. Because the DoD's been spending big bucks on this stuff for the last 30 years. So when you see a cluster of drones, and you see like movies where there's a drone and a missile and an airplane, and they're all working together to try to blow somebody up, that's called coordinated control. And to the degree that that's automated, then it's an AI, and they're doing distributed consensus to do that. So that's my background. That's what I work on. So I want to talk about that a little bit, so you guys get a sense of why that's an important one that you've never heard of, but it's probably the most important one for the applications that we have in building applications on the blockchain. Because coordinated control is what we want to do. What is coordinated control? Another word for it. People working together in teams, in groups, and coordinating their activities so that they all work together to come to a predicted result in an environment of uncertainty. So this is what I did for the first 10 years of my career. I built these things. So these are autonomous underwater vehicles. So these are self-driving submarines. No humans in them, fully autonomous. This is 90s. So back then, this was like really hard to do. It still is really hard to do because you don't have GPS, you don't have Wi-Fi, you don't have any kind of communications. It'll never not be hard to do. But the Navy had a real interest in this because shallow water mine reconnaissance is a really dangerous thing. And so until AUVs, if you wanted to clear a path from offshore to onshore so that troops could land to attack somebody, you wanted to clear all of the sea mines along that path, because they don't really want to repeat Normandy, right? The invasion of Normandy, where you lost half your troops before they even got to the beach, right? Because of things. So the approach in the 90s is Navy SEALs, not animal SEALs, humans, in scuba gear, which means you have a limited time underwater, in the dark, with kickboards, with a little sonar that was low resolution, that they would swim, and they go like this, and if they saw a mine, they'd give them a blip, and then they would have to mark it. They'd have to know their position because they didn't have GPS. They'd have to try to figure out where that was, remember it, right? Swim back, and then the next guy, and they would take several hours to clear maybe 100 feet, right? So to do like a mile in from shore might take them 2 weeks. And the whole time they're in coastal waters, and if a boat comes by or sees them or something like that, and if they get lost or they just get confused, right? And they're in the dark, and they swim into a mine and bump into it, bad things can happen, right? So that was the problem. So it was worth the Navy spending a lot of money to try to automate that process, right? So that's the background. So, and then there's environmental adaptive sampling. We also did shipboard automation, building automation. This is some of the stuff there. More recently, I did this project, which is physical security of critical infrastructure. This is a robotic controlled non-lethal actuator with radars, so that if an armed insurgent tries to attack this, it will blast them with this sound blast that will make them very uncomfortable enough that they want to leave without killing them or blowing up their eardrums. So AI for control is all about making groups of people work together in a positive way, right? So when you talk about malicious actors, how can we get people to work together despite the fact they're malicious actors, despite the fact that there's noise and uncertainty? Almost all smart contracts are based on certainty, right? Under the hood, they're all Boolean. I make a decision, yes or no. But in the real world, it's not Boolean. So somehow I have to take information that's not Boolean and translate it into Boolean information for a smart contract to execute. And that's what distributed control is all about. Coordinated control is all about operating in environment efficiency, but still have computers that are making Boolean decisions work. So you see structures like this. This is the sort of architecture that you build in your software, something where you have different layers, different types of processing that's happening at the different layers, and you can refactor it this way, which is a layer run with an arbiter. I'm not going to spend a lot of time on that. I just want to expose you to the fact that there's a lot of meat here that nobody is using. Nobody's even thinking along these lines, because most of the people that are in this space don't even know blockchain exists, right? They're like, oh, what's that? So groups of autonomous agents from different circumstances cooperating to achieve shared objectives in environment uncertainty. That's the problem. Does anybody have that problem? Some people do, okay, right? Does everybody have this problem?
Yes.
Yeah, okay.
Just that seems like the definition of an organization.
Yes, exactly. Well, what is an autonomous group of vehicles, right? We're not talking about a single vehicle, we're now talking about a group of vehicles that have to, that's what coordinated control is. I've got a group of autonomous vehicles that have to coordinate to solve an objective, right? So when I think about projecting that to blockchain, I have groups of autonomous agents. The agents might be persons, they might be software agents. They all have to interact together to solve a problem. So decentralized, well, you just said it, right? Distributed autonomic services. I like the term autonomic. The difference between autonomous and autonomic is base level stuff that keeps you alive. Think of your autonomic systems: breathing, your digestive tract, your blood system, circulatory system. Those are all autonomic. You don't have to think about those. They just work and keep you alive. Many of the things that people are building are actually autonomic services. They're to keep something alive, keep it functioning. It's not at the high level. The high level is still humans making those decisions. They're thinking about it. But until you have the autonomic services, this stuff doesn't work very well. And so in an autonomous vehicle, you start with these. And then you layer on the mission planning and the high-level decision-making after you get this work. And it doesn't do any good to have a vehicle that sinks, right? And if it gets a leak, you gotta, bring it back or something, And so a lot of failures that people have is that they give short shrift to this stuff. They just assume everything's gonna work. They assume there are no bugs in their code, there are no memory limitations, somebody's not gonna fat finger something, and they just make those assumptions, and I gotta get the MVP out, right? So for us, if we went to C with an MVP, it means that was the only time we went to C, because we lose our vehicle and we'd have to go back to a program manager and say, hey, we just lost a $500,000 vehicle, you wanna give us that another $500,000? You go, no, thank you. In fact, I was at C once, and it was they called it a bake-off. So the program manager had a bunch of different AUVs that were doing different things. And one of the groups that he had funded was there with their vehicle, right? It's the first day we're at sea, and everybody's prepping their vehicles because we're going to run missions and do performance bake-off between what they were doing. So a lot of people were doing sort of like staging runs where they put it in the water and make sure the motors work and stuff like that. So the very first day, this guy puts his vehicle in the water, right? Doesn't do anything, right? It's like, oh gosh, must be bugging my code or something, right? Pulls it out of the water on the deck in front of everybody, right? He goes and he cracks open the hatch, salt water comes pouring out. Oh. He was done. He was done. It fried everything. He was done. The rest of the week he didn't do anything. It was like as embarrassing as you could be. You didn't check your O-ring seal before you put it in the water. You just assumed that it would, it's a little hair, not enough grease, whatever it is, right? So there are different approaches to coordinated control. So what do you think the first one is that anybody would think of if I wanted to coordinate control? How would I structure it? Hierarchical. And what would I have at the top of the hierarchy?
Boss.
The boss, right? Leader follower, right? I have a single leader, makes all the decisions, tells everybody else what to do, right? Simple. There's no distributed consensus, there's no multi-objectives. He makes all the rules, right? The next one is called behavioral. Behavioral means that everybody has a set of rules, and they all act independently, but the combination of the rules allows them to have some sort of coordinated behavior, right? And we'll talk about those in a little more detail. And then the third one is a role-based one. And this is really the state of the art now for this. So let's talk about let's see what those mean. Full state of the leader is broadcast to the followers. Think practical Byzantine fault tolerance, right? It's a leader follower. Leader sequences group tasks. Followers execute a formation relative to the leader. Makes it really easy to get mathematical guarantees because if the leader's correct, then all the followers are correct. It's centralized. Oh, bad word, right? Fragility, communication failure, member loss. It's really hard to do heterogeneous behaviors. That means where I want some followers to do something else or not. Or now I got to have multiple leaders, right? So now I have to reconfigure it to have multiple leaders if I want to have different behavior, right? So let's look at behavioral. You probably haven't heard of this, but there's something called this assumption architecture. It was really popular back in the 90s, a layered approach, and it was really successful for a while, but it has some limitations. So you give people behaviors, and then you take a weighted combination of the behaviors which are a function of the environment to decide what you want to do. It's almost impossible to analyze or guarantee performance because it's completely environmentally dependent. So you have to simulate the heck out of it, right? Which is what a lot of people do with trying to build trading systems, because all the people interacting on the trading platform all have their own set of behaviors. It is decentralized. It's robust to communication and member loss, but it's dependent on environmental coherence. And precise coordination is really difficult. So things like swarming and flocking work really well. You ever seen a flock of birds or a swarm of fish? You can build those really simple. The rules are really simple. Like if there's something in front of me, follow it. If there's nothing in front of me, look for food. Right? If something's to the side, don't hit them. Right? Just those set of rules, and I get a flock. You put those rules in a bunch of simulated birds, and they will form these really complex swarms and stuff like that, just from those set of rules. So it seems really powerful, right? People are really excited about it. The problem is that if I actually want to do something more precise than just swarms or flocks that are flying around, I can't do it. So virtual structure or role-based is actually kind of in between. And the way role-based works is that I have a peer-to-peer network. Every peer has a local state, but everybody is sharing their local state with their neighbors. And each person can have a different, or each node or each agent can have a different role within the group. And so each role then has a different set of rules. So it's a combination of those two, and everybody has a shared set of objectives. So it's like the adaptive critic. You've got this objective function that says our goal is to kill that thing, right? So it's a flock of, it's a swarm of drones that have to converge on a point and drop their bombs or, whatever their thing is. Or it's a bunch of people that have to decide to vote for something, make something on your platform get uprated, right? So you have to have this global shared task sequencing. The way that works is that you have a mission, right? So the task sequencing comes from evaluating where you are in the sequence relative to where you should be, and then trying to make sure you fit the sequence. You know where everybody else is, so you can adapt. So one of the classic problems is time over target. You want to have a bunch of people meet at the same place at the same time. They start at different locations, so they have different distances to get there. So how do they adapt their path so they all arrive at the same time? And given that there might be things that happen. So if you think about a group of people, group of nodes, group of agents working on your platform, that start in different places but need to come to consensus or need to come to a shared activity, then this is appropriate to that. So you get a consensus function that is cohering the state information so that everybody says, okay, we all want to come to agreement, we all have different opinions, but what we're going to do is use the same algorithm to get our opinions to get closer together. So it's a type of distributed consensus that is agreeing about the state of nature. You're agreeing about what the current global system state is and where you are in that. And so you can use like a Kalman filter, recursive least squares, some kind of weighted average. All of those are algorithms that are other branches of AI or signal processing that you have to know about to do this, but it's there, so you just know what the words are. Am I out? Oh, gosh. Okay. Anyway, it's decentralized, robust communication, allows coordinated autonomous behavior, and can be hierarchical because you can have hierarchical roles. So you can still have a leader if you wanted one, but only did certain things. And, and it's scalable because it can be hierarchical. So anyway, that's an example of a role-based coordination and control architecture, and I'm out of time. So. At 4, I'm giving a session on reputation systems. So we'll go deeper into a specific branch of an AI that applies to this.